Okay, yeah. So hi everyone. My name is Prisha Marpu once again, and my project revolves around using machine learning to classify cardiovascular disease. So just a little bit about myself. I'm in the class of 2025, and I'm from the Bay Area in California. And my mentor who helped me out throughout this entire project is Vidya G. So just a huge shout out for her. And I've been interested in this project, especially because it's like a middle ground between machine learning and the healthcare systems. And it's a great way to kind of bridge the gap between patients and the medical officials as well, and just make the system a bit more efficient. Um, so what is cardiovascular disease? So the main thing that anyone would want to know to start off with is that it's the leading cause of mortality worldwide. So as we can see in this image here, around 33% of all deaths in the past year were due to heart disease. So heart disease is just another way to say cardiovascular disease. And it's such a big, it's like a wide range. So you have various forms, subcategories in the disease. So let's go through like briefly what each category would entail. So first of all, we have coronary artery disease. So this is where the blood vessels become too narrow and blocked due to plaque buildup. And then we have heart failure, which is a little bit more mild compared to the um, rest of them. And this one's focused on when the heart is unable to pump effectively. And then we have stroke, which is when blood flow to the brain is blocked or reduced. And finally, we have arrhythmia, which is the one I'm like mainly focusing on in my research, which is when you have abnormal heart rhythms. So this could be like your heart is beating too fast or too slow in comparison to like just like the regular normal pace it should be going at. Um, so like at the moment, there's a lot of treatment options for patients with arrhythmia. Like we have beta blockers, electrocardiogram, pacemakers, and just like the general ECG monitoring systems. Um, Although we have such an like extensive treatment system, it's important to shift focus from like playing defense all the time and actually going into offense and trying to get there as early as possible to detect and just like limit the amount of time and effort and kind of like uh, emotional effort that it takes to deal with the arrhythmia over time. So as we can see by cardiologist John Doe, he says that early detection of arrhythmia is crucial as it allows for timely intervention, potentially preventing life-threatening complications such as cardiac arrest and stroke. So cardiac disease is pretty intertwined. So one thing could lead to another. So the best thing we can do to limit any further implications is to detect it as soon as possible. So yeah, now that we know what the problem is, how could we use machine learning and technology to help with this? So this is like the basis of my entire project. And what I set out to do is use CNN models, which are basically going to take previous data, which I got from an MIT database containing around like 40 to 50 patients and their ECG data. So I'm going to be using their data and trying to create like a prediction system that allows any future ECG data to be classified as well. So there has been a lot of past research done similar to what I'm trying to do. So we have Eddie Mina, who did a similar project using 1D convolutional networks. And she created a model with 98% accuracy, which is pretty impressive. But what I wanted to do is build off of her project and try to classify specific beats rather than the patient as a whole, because her project focused on classifying the patient as a whole of what they could potentially be having. Rather, I wanted to look deeper into the specific pieces of the ECG data and show if this section shows a normal trend or this shows like particular contraction, for example. So there's a lot of machine learning models available in today's world. So why did I choose CNN specifically? So this would be because CNNs are used to find trends over a period of time. So typically you would have heard, if you've heard of CNN, you would have seen that they've been used for image classification. Like for example, if you were to do like cancer prediction, you would use a conv2D layer. But since since we're trying to classify more like a data set, like numerical values rather than physical images, I used a conv1D layer, which is designed specifically for a time series data, like the ECG data that we have here. And the job of the conv1D is to kind of zoom in to specific pieces of the data and try to identify trends, and then zoom out again and try to generalize the trends that it found. So in this process of doing conv1D multiple times, you get a final shrinked response between 0 to 8. And this output would tell you what kind of classification the model is giving us, right? So let's look into some examples of what this could actually look like. So for example, on the left side, we have a normal heartbeat curve, while on the right side, we have a abnormal heartbeat curve. So just right off the bat, physically, we can see that there is a dip in the second one. So what the model does is it doesn't take the image, but rather the numerical values, like the amplitude, for example, of each peak, and it connects it to into the beat before as well as the beat afterwards, and sees what is the differences or similarities that we can see in these beats. So in this example, we have the fourth beat, which is a little bit lower than the other beats. And then the fifth beat is much, much higher. So just noticing that there is a big jump in the amplitude, the model is able to identify that it should probably take a closer look into that specific region. And once it does this, it goes into the data once again and tries to zoom further in to see what changes are happening. And once it has a general idea what's going on, it will compare this piece of data to the next piece of data, next feature or next patient as well, and try to connect the dots between those patients as well. So this could be a little confusing just with me saying it out loud. So let's take a look at an example. So this is from patient 214. So what I've done is I've taken one instance where there was some sort of abnormality. And I took 10 data points before and 10 data points afterwards to see the visual trend that is happening before there's an abnormality. And that is what I store in a feature list. And then I have a type list that classifies what that feature is showing. And I plug in this feature and type list into my CNN model, which is shown below. And as we can see with the inputs and outputs, we initially start off with a 21 element input, which is just our regular feature list. And then through the process of shrinking and widening, we get to an output of 8, like I mentioned previously. And the reason why you're probably wondering we're shrinking and then just bringing it out again is because we want to zoom into a specific piece, identify the trends, and then zoom back out to just generalize that trend to a bigger picture. And then finally, we don't want our data to get too extensive. So we have to shrink it further using a linearity and have an output of 8. So you're probably wondering, what do these numbers mean? I mentioned multiple times that you get an output between 0 to 7, right? 8 values. So you don't get 8 values as an output, rather you get one value between the range of 0 to 7. And each value represents a different classification. So for example, in our previous example for patient 214, they have a type of 0, which we can classify as normal. So this is also just a visual representation. Once I graph the patient's data, we can see a lot of the beats are normal, but we do have a couple V's, slashes, and A's. So once this model gives out this output, if there are a large number of irregularities, it's up to the patient to go to the doctor and actually get it checked up. Because although a model is a great tool, it is not 100% accurate. So it's always best to go to a doctor first and actually get clarification. So this is just a tool to just give patients a little bit more like early like knowledge of what could potentially happen. So to end off, what are my future plans? So I've built a model with pretty good accuracy. So what I want to do in the future is try to just improve the accuracy and try to get it to maybe like 95 or 96 or even 100 potentially. And also try to branch out the data that I'm using. So for now, I used the MIT database, which has around 50 patients, like I mentioned earlier. But each patient has around 6,000 data points. So that is a lot of data, but we do want to branch out and look at more patients, not just from that specific region of America, or maybe just like from the West Coast as well, or like around the world. And the final thing that I would like to do in the future is connect this model to like maybe a physical device and allow it to be more like a real-time classification rather than you having to like import your data. So this would just create a more a faster and sustainable alternate. Yeah, so thank you so much for listening. I hope you enjoyed my presentation.
Thank you, Prisha. That was fantastic. So we have quite a few questions coming in Q&A. So let's answer a few of those.
Okay, yeah.
The first question that I see here is, what are your plans to evaluate the model? Like, what metrics do you plan to use? And what are your thoughts on patient data privacy when using such ML models for disease prediction?
Yeah, so to start, that's a great question. To start off with the first one, I think that like the patient like privacy is not really an issue here because we're not taking any like specific like personal like information, rather just like the heartbeats. So it won't have any direct correlation with the patient themselves when I'm making the model. So if a new patient is using the model, it is their choice to input their data, but we're not taking in any like name, address, or things like that. It's just the heartbeats. So even there won't be any like misuse of that data when it's used by the model. Oh wait, could you repeat the first question again?
Yes, of course. The first question was, what are your plans to evaluate the model? Like, what metrics do you plan to use?
Oh yeah. So what I plan to do to evaluate this is, since I've created a model using around 50 patients, I will use another set of data from a different patient that the model hasn't already been exposed to. And then while I plug it, when I input that data into the model, I'll give out like an accuracy percentage and validate like what percentage of the classifications are actually accurate to what they are medically like described as. And so typically what we see with like machine learning is that the model like memorizes the data. So when it's exposed to like a new set of data, it's unable to classify that. So I've tried overriding this by inputting new set of data so that it's not just, so I can just check if it's not just memorizing and like giving like a high accuracy through that. So I have done I put some effort into like decreasing like the overfit for that. Mm-hmm.
Thank you. Thank you so much, Prisha. That was wonderful. Thanks for presenting, and thank you for those wonderful questions as well to attendees.